Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good webinar on computer vision for the next generation of autonomous robots organized by the ITU. This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping to unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. Without further ado, I would like to introduce our moderator today. Her name is Karen Panetta, and she's the Dean for Graduate Education at the Tufts University School of Engineering. Karen, welcome, and the floor is yours.
Thank you so much, Guillem. It is an honor to be here. I'm your moderator today, and we have assembled a world-class panel for you of panelists and everything AI. So if you think about what's going on today, artificial intelligence is dominating in every aspect. We're buried with sensors all around us, in our life, in our health, everywhere. And we need to make sense of the massive amounts of data that are out there as well. So how do we take all this data, all these sensors, and use it to benefit humanity and to bring truth and explainability to all of those who use it and trust it? So with us here today, I'm going to have our first speaker, Dr. Peter Cork. He's a distinguished professor at the Queensland University of Technology. So Dr. Cork, take it away.
Thanks very much, Karen. All right, let me just share my screen. Okay, can you hear me okay?
Yes, we can.
Good, go for it.
Perfect. All right, thank you. All right, thanks very much, Karen, and thank you very much to the organizers for inviting me to this wonderful event. What I'd like to do is to talk about the problem of robot hand-eye coordination. And I probably should say at the outset.
Very quickly jump in. We can only see part, a little bit of the presentation. So if you could expand that so we can see the whole screen.
All right, let me go and share again.
Make sure you're in presentation mode, like slide mode.
Yeah, I was. All right, guys, sorry about this. Back to meeting. Sorry, I can no longer find my Zoom controls. There we go. Stop sharing.
We need AI to help us run our Zoom sessions and all
Yeah, we
that.
do. Sorry, I'm really rusty.
If you go into the share screen.
Yeah.
Okay.
Step one. How's that?
Perfect.
All right. Apologies for that. All right. I'm going to talk about the fairly narrow problem of robot hand-eye coordination. And I should say at the outset that this business of using computer vision to to control robots is something like a 7-decade journey that many of us have been on. This is a really, really hard research problem, and I'm going to talk about just one small part of it, robot hand-eye coordination. And this is work in conjunction with my postdocs and PhD students. So there is this massive disparity in our ability to solve very classic AI problems, perhaps those that are best solved by massive search, and to be able to manipulate things in the physical world. So use the example of computer chess, 1997, that's many decades ago now. Computers have gained the ability to be better than humans at this pursuit that I guess for the longest time we thought was like the pinnacle of human intellectual endeavor. Yet, in contrast with that, a small child could probably pick up a chess piece and manipulate it, maybe not know how to play the game of chess. You could pick up a manipulated chess piece. And that's something I would argue is something that is still beyond our ability to do with robotics, to do this hand-eye coordination to pick up a particular chess piece. And maybe we could engineer a solution to that particular problem. But I would argue that it probably wouldn't generalize very well. And if you put a chessboard in front of a robot vision system with different sorts of chess pieces, maybe they were transparent, made out of different materials, the engineered system would very likely fail. Yet a small child probably would succeed. So there is this interesting paradox, I think, that purely intellectual activities, AI systems, computers can solve very nicely. But this physical problem where AI meets the physical world is still really beyond us. And I would argue that hand-eye coordination is a human superpower. And if we can get robots to perform this very, very human capability, then they'll be a lot closer to the useful machines that we all dream about. And I show in this particular slide a number of examples of things that humans do by essentially hand-eye coordination. The driver is taking visual information and mapping it into steering wheel angle and accelerator pedal positions. And the jugglers down the bottom are doing amazing things that involve prediction of dynamic objects in the world so that they can move their hands in order to perform the task. We can do some of these things using computer vision today, but we're still a long way from the fluidity and gracefulness and, if you like, visual intelligence that human beings have. And I always like this particular example, which is a problem human beings can do with almost without any effort at all. Thread a piece of cotton through the hole of a needle. And we do this without doing the sort of traditional things that a roboticist would do. We do this without estimating the pose of the needle, without estimating the pose of the piece of cotton. We just move our hands so that those two things come together and the task is done. It's not the way we do it with robots is still very clumsy, inefficient, and complex. So in my particular lab, we've been looking at hand-eye coordination problem for a long time, and we started out with the simpler problem of reaching. That's just how does a robot reach towards an object of interest, not trying to grab it at this point, just reach towards it. And this is some work we did with neural networks back in 2016, a network that takes visual information and synthesizes robot joint velocities directly. From that, we did another generative network, takes a depth image and synthesizes directly in about 1/30 of a second the place to grasp the object and the orientation of the robot's grip of fingers in order to successfully achieve the grasp. So unlike many of the traditional approaches to grasping, this directly synthesized grasps 30 times a second. And here's an example of it, reaching down towards an object that was initially moving. And it will just relentlessly go and clear the table here, just find the most graspable thing, then the next most graspable thing, and so on. But a problem with this particular system is that it's limited by the sensor. The sensor's got a limited field of view. It's got a limited working range. When the sensor's too close to the table, it goes blind. It's a limitation of a lot of depth sensors that we use in robotics. So we started to think then about where's the best place to be looking at the world if we want to do a task like grasping. And traditionally, we have the camera either fixed in the environment looking at it or on the robot's wrist. But depending, those two particular configurations are very prone to occlusions from objects in the world. And we proposed actually a better place if you wanted to picking up objects in the world. The best place to look is where the fingers are actually interacting with the objects. So rather than doing this sort of anthropomorphic design, we should move the eyes so they're very close to the fingers. And that seems sensible at face value. They're very close to where the action is during grasping. But the problem is, how do you prove that that's actually better than the traditional camera placement? So we did some work with physical benchmarking. We came up with some random trajectories and a mechanism to move objects. And then we could compare camera placements directly. So in this first example, the robot's trying to pick up an object and it's got no prior knowledge of where the object is. It can't, and it's got limited ability to predict it. If it goes out of the field of view, it's lost it and fails in grasping. By contrast, if we put the fingers so that put the cameras so they can observe the fingers, then the grasping is much more robust, and we don't lose it nearly so often. So we can say in a very quantitative way that there's an advantage in putting the cameras looking at where the grasping is actually happening. I mean, there's a nice camera eye view of the robot swooping in, picking up an object. And then we sort of integrated that technology with a dynamic reactive planning framework that we developed in the lab, and led to some very nice whole body control. So what you see here is not actually the result of a traditional motion planner. This is an emergent behavior of the robot, just simply moving from a pickup station to a drop down station. Then we started to think about the whole business of picking things up and putting them down. It's a very common operation that we do. And when humans do it, they do it in a very fluid and graceful way, where this is a relatively recent video from an IROS conference, and we speed it up by a factor of 10. And we can see that the robot has lots of long pauses. And these are predominantly the robot stopped to do planning. And so it's taking a picture of the world, reasoning about it for a long time, doing an action, reasoning about the world, doing an action. And this looks very unintelligent, to be honest. And what we decided is we should start to focus on fast, intuitive motion. You'd want to work with a robot that behaves in a way that is intuitive. I think that would be very helpful. So we started to think about the problem, how can a mobile manipulator pick up objects without stopping? So just drive past, move its arm, grab the object and keep on going. And here's an example, an early simulation of a robot doing exactly that. So it's trying to pick up an object on a table. That object is actually moving with respect to the table. We plan a trajectory to swing past and pick it up, and we use hand-eye coordination to deal with the motion of the base. Here's an example of this. We have the mobile manipulation platform, and it's simply trying to clear all the red cubes off the table. There's a little robot in the foreground wearing a shirt, and that's simply acting as a dynamic distractor. And this robot is planning, comes past the table, attempts to pick up each object without actually stopping as it's going along. So we've kept working on this particular idea of what we call manipulation on the move, integrated with hand-eye coordination. And these are some very recent results then from the lab. We're starting to be able to give descriptions of tasks in a very high level way, ask the robot to get a bottle of water from a cupboard. It knows where the cupboard is, will come in, open the door, and then reach inside the cupboard to grab, for instance, a bottle of water and take it to where it needs to go. So these are just a few examples of robot hand-eye coordination. And I think hand-eye coordination, the ability to move, to pick up things on the move without stomping, are all important characteristics of robots if they're to achieve human-like performance. Technologically, it requires a combination of very flexible planning and appropriate computer architectures to process the data that comes from visual sensors, particularly cameras. But what I haven't had a chance to talk about tonight is how we fold in additional information, particularly force and tactile information, for what you might call the last nanometer problem. We can use cameras to guide the fingers very close to the object, but as soon as we make contact, that transition between open loop and contact, forces come into play, and we need to deal with those in order to get decent robot performance. So I'm going to stop there, and I'm happy to take questions later on. Thank you.
Thank you so much for that. So, you talked a lot about, there's a lot of sensors out there, a lot of manipulators out there. So, and trying to bring it all together. So our next speaker is going to really address some of these issues with cameras versus, all the information that's there and visual sensors, and how do we use this type of information quickly to make decisions and implement actions. So at this time, I'd like to introduce Dr. Luca Calone. He is a associate professor at Massachusetts Institute of Technology. So Dr. Calone, the floor is yours.
All right. Thank you so much for the kind introduction, Karen. It's a true pleasure to be here. So my plan for this short presentation is to give you a quick overview of some of the work in my lab on robot perception and vision-based navigation for the next generation of autonomous robots. Before doing that, let me use this slide to acknowledge the students, collaborators, and sponsors contributing and supporting our work. None of what I'm going to present was going to be possible without them. So we'll just start by remarking that we are living in a unique time, a time where robotics is already impacting our everyday life. Robotic technologies are powering the self-driving cars that are driving in some of our cities. Millions of robot vacuum cleaners are sold every year. And mobile robots are already handling warehouses and enabling us to get our products shipped in hours. Similarly, as you see in the middle of this slide, aerial robots have a huge potential for monitoring, inspection, and disaster response. And robotics technologies are increasingly deployed for precision agriculture. Moving to the bottom of this slide, robots are also enabling our efforts in science exploration from space to the ocean's depths and more. And you can easily understand that the reason for this breadth of applications is that robots are simply faster, safer, and cheaper to deploy in many of these applications. As such, robots have a key role in contributing to the UN Sustainable Development Goals, including zero hunger. For example, I mentioned already precision agriculture, decent work. For example, there is an application here in mining for robotics, life below water and land, climate action, and many, many others. There is a role for robotics in all this. At the same time, we have to realize that with great power comes great responsibility. As the deployment of robots increases, we have to make sure that they can reliably operate around people. And in this slide, I'm showing a number of failure modes of robotics applications. In this case, I'm focusing a little bit more on self-driving vehicles as an example of application. So the example I have on the left is a picture from March 2018, where a self-driving Uber vehicle failed to detect a pedestrian and provide a warning to the emergency backup driver, killing a woman in Arizona. The one on the right is another example at the top right from 2018. Here, there is a Tesla Model X failing to detect a concrete barrier on the left of the car and deciding to turn into it. The autopilot decided to turn into it, killing the passenger on board. And at the bottom right, there is a popular example many of you might know. At the bottom right, of course, you see stop signs. In regular conditions, a neural network will be able to classify and to detect these as a stop sign. But if you place very carefully these black and white markers on top of the stop sign, you can mislead a neural network to confuse these for a 45 miles per hour speed limit, which is a very bad mistake to make at an intersection. So this example go back 2018 and so on. The unfortunate thing is that things haven't gotten much better since then. And indeed, I'm putting a couple of examples on the right, which are more recent. The one at the top is about the phantom braking issue with Tesla going back to February 2022. And at the bottom left, there is a problem with Cruise crashing into a fire truck in August 2023. As you can see, many of these failures can be attributed to failures of the perception and computer vision systems on board of these robots. Therefore, we really have to develop more robust and trustworthy perception systems. This has been one of the key motivations for the work of my group. So one of the key tasks my group has been working on is to develop what we call certifiable perception algorithms and systems for safety critical and high integrity applications. In my lab, we have taken a multi-pronged approach, starting from algorithms and defining the notion of certifiable algorithms. Of course, I will not have time to enter into the technical details, but a certifiable algorithm is an algorithm that is computing an estimate, for example, for the pose of an object in the scene, and is either certifying that the estimate is optimal and correct, or is detecting failure otherwise. Again, we have been testing these algorithms and this idea to more reliably detect objects and vehicles, for example, in self-driving car applications. And this idea is worth mentioning. They build on novel tools from mathematics, including moment relaxations. At the second level, we have been more recently investigated the fact that the idea of certifiable algorithms also enables self-supervised learning. The insight here is very simple, is that if you are able to distinguish correct estimates from incorrect ones, we can learn from the correct estimates without human supervision. And that's really enabling self-supervised learning. At the next stage, we're moving from algorithms to system-level reasoning. And we've been tackling the fact that the perception system really consists of several interconnected modules and algorithms. Therefore, we took a more of a system-level view of a perception system and developed tools for runtime monitoring and fault detection in complex systems, for example, the ones that you face in self-driving vehicles. Building on top of this foundation, my group has been particularly active in releasing fast open source implementations. You can find them in our GitHub organization that you see on the left. My lab is called the Spark Lab, and you can see the link to the GitHub organization. And many of our algorithms are now part of standard libraries, including GTSAM and MATLAB. Finally, one of our motivating goals has been to showcase really our algorithms working in the real world. And I'm just putting 3 examples of application at the bottom of the slide. We've been lucky enough to have the chance to compete in the DARPA Subterranean Challenge that you see on the left. Here, the goal was to demonstrate autonomy in underground environments as the one that you encounter, for example, in search and rescue. And we've been lucky to team up with JPL and compete in the DARPA Subterranean Challenge, where we were first and second place in 2 of the 3 competitions. We've been also demonstrating our certifiable algorithms and system-level monitoring capabilities in self-driving applications in collaboration with Ford and NVIDIA. I'm putting a snapshot in the middle of the slide. And finally, we also worked on high-integrity applications, such as terrain relative navigation, where one of my students was lucky enough to fly some of his algorithms in collaboration with Draper on the rocket that you see on the right, which is Blue Origin New Shepard rocket, again in collaboration with Draper. So this is a quick summary of some of the work we're doing on improving safety and developing this idea of certifiable perception algorithms and systems. Next, I will switch gear and I will introduce the second research thrust in my lab, which has been about developing human-level perception capabilities and real-time scene understanding algorithms for robotics. So the observation here, which is something that you've partially seen in Peter's presentation, is that traditional mobile robots really understand and execute fairly low-level instructions. For example, you can tell the robot go to position X, Y, and Z. This is because they mostly understand the geometry and geometric aspects of the environment they move in, which allows them to avoid obstacles and reach a desired location. However, in my lab, we've been thinking about the next generation of robots, and we would like for the next generation of robots to understand and execute high-level instructions, such as robot, go search for survivors on the 2nd floor of the red building, or maybe robot, go grab me the cup of coffee on the table in the kitchen. In order to parse these instructions, the robot will need to form a complex model of the external environment and understand what is a kitchen, what is a cup of coffee, and how to reach them. This goal of enabling high-level task execution motivated a lot of work in my lab. And in particular, towards this goal, we've been working on going beyond traditional SLAM and towards spatial perception for robotics. For those of you who are not working in robotics, SLAM stands for simultaneous localization and mapping. It is a foundational problem in robotics and is mostly about creating a geometric map of the environment as the robot explores it. Here we are arguing that we need more than SLAM. We need spatial perception, where the goal is to create a human-like understanding of the external environment for our robot. So along this line of work, we have developed several methods that allow a robot to understand complex scenes in real time. The first one was Chimera, a real-time approach that uses camera images and reconstructs in real time a 3D metric semantic mesh of the environment. So the geometry of the mesh describes the obstacles in the scene, while each phase of the mesh is color-coded with a semantic label. For example, in this video, the robot is building a mesh in real time, and the different colors correspond to different types of elements in the environment. For example, the yellow are the cubicles, light green are the couches, dark green are the walls. Again, different colors correspond to different type of objects. And the robot can do this on a CPU, like on a small compute budget, and in real time. More recently, we have been developing more complex map models called 3D SIGGRAPH, in which the robot not only understands the metric semantic mesh of the environment, but can also reason over objects and agents in the environment, as well as rooms, buildings, and so on. And we have been able also to develop the first system called Hydra, which is a system to build a 3D SIGGRAPH from sensor data in real time. So here in the video, you see a robot exploring the environment, building this metric semantic mesh, understanding objects in the environment and reasoning over the relation between objects, and understanding that, for example, the room it is moving in is a kitchen. Okay. And of course, I will not have time to mention much about these systems, but they are really bridging traditional geometric understanding and SLAM with deep learning, graph neural networks, and large language models. We've been developing and deploying many of these methods in several applications, including applications to multi-robot systems exploring unknown environments, systems interacting and manipulating the environment, as well as systems operating near humans. I'm particularly excited about the work we have done on soft aerial manipulation, where we use perception to guide aggressive grasping of objects with a drone, as the video that you see here in the middle of the slide. So we wrap up with the final slide here. I want to conclude with a slide that is summarizing the type of capabilities we aim to develop for our autonomous system, and somehow summarize what I told you so far in this presentation. Towards this goal, I'm going to show a video. This is not a real robotics feed, it's a computer rendering rather than something that is currently possible, but it still highlights some of the key components we want to develop. So in the video, you see a small drone with onboard cameras, a number of small drones able to effortlessly move among obstacles and perform vision-based navigation. And so the first element is vision-based navigation. As you see this video, you also realize that there is another thing that stands out, which is how these drones are interacting among themselves and with the environment and are able to execute complex actions. So the second element is interaction with the environment. So towards getting advanced vision-based navigation and interaction with the environment, my lab has been working on the development of certifiable perception algorithms to increase the robustness of robot perception systems, and has been also working on human-level scene understanding to enable robots to perform complex navigation and interaction tasks. In our work, we combine fundamental insights with open source implementations, as well as real deployment on actual problems. So if you want to learn more about the work in our lab, feel free to follow us and reach out. And thanks for your attention, and looking forward to the panel discussion.
Thank you, Dr. Calon. That was fabulous. Next, we're going to talk about 3D perception, more robot manipulation, and language understanding with our next speaker, Dr. Katerina Fracadiadaki. So Dr. Fiadaki, take it away.
Yes, thank you very much. Thank you for inviting me. I just shared my screen. I think you can see it. And so we'll discuss, I'm just going to continue from our first previous speakers. The talk may be more technical than the previous two. So where are we and how far are we from, building, capable robots? And I think Wall-E was pretty capable in the movie on recycling, figuring out the objects, manipulating them, and so on. My talk has two parts. First, I'll discuss 3D perception for robot skill learning and learning from demonstration specifically. And second is how can we automate and supervise that demonstration collection so we don't need to ask humans to show us how to do things, right? So let's go in the first part. My lab, the last few years, works on 3D perception. Images, the pixels show whatever is visible, but we know there's a big part of the scene that is not visible. Here is the rest of the cut. So how do you capture that? So we have developed differentiable neural network architectures that map those 2D images, what you see here, to 3D feature maps. So these maps are 3D grids of, X, Y, and Z, the depth, and every location has a feature vector that describes the content of the scene. So these are very similar to the maps that Luca talked about, but they're trained in an end-to-end differentiable way and self-supervised with view prediction, as I'm going to show. So every location on that map has a feature vector that describes geometry and appearance properties of the scene. And you can train those networks end-to-end, much like you train your 2D convolutional networks or 2D transformers to detect 3D objects in the scene. So these 3D features learn to capture whatever is relevant for your task. And we know that the problem with those 3D maps is their spatial resolution. You really want to be super accurate, and this may blow up your memory. Okay, so you can combine, instead of just in every location ijk, you're saving a feature vector, rather you can parameterize a function locally where you feed it an XYZ and that function predicts a feature vector. And in this way, you can have an infinite continuous spatial resolution for your 3D feature maps. Now, the same way you build 3D maps by a moving camera, we have robots that either have multiple cameras mounted on them or have one camera moving or both. Then you stabilize that contact the way I described with those networks. You can also squish the vertical dimension and have a two-dimensional bird's eye view map. And this is precisely what is being used right now in self-driving cars, this type of architectures. And what can you predict? Well, to drive, you need to know the lanes and the traffic signs and where the other cars are and so on. And our model does very well in comparison to previous works. And I just want to show here a small snippet from a Tesla presentation a couple of years ago, where they compare, if you take all these perspective images and first infer labels and then fuse the labels, that you get these artifacts on the left that you cannot drive from. While if you just featurize the images and then merge them in geometrically consistent way, then you can predict outputs that the car can drive from. So I think our self-driving cars currently are like the most capable and intelligent robot out there. It really can handle a wide, pretty open-ended set of situations. So since we have seen this, I would say, success, with enormous amounts of resources spent and wasted, unfortunately, due to the lack of sharing between the different companies that develop these technologies, what can we learn from self-driving cars to put them into robot manipulators? Okay, so since 3D perception can be so important for self-driving vehicles, what about robots? Can we use similar ideas to be able to learn skills from very few demonstrations? This is what we want. We want to be sample efficient. With very few training examples, we want to have very high performance manipulation policies. And I'm going to show you now an architecture about to be published in Coral in 2013, we call Act3D, which has state-of-the-art performance for learning manipulation tasks with a very big jump with respect to the previous state-of-the-art. So here is how it works. We have a task that is described here in this instruction, and we have a robot that can see the scene from a number of cameras. Okay, so here is 3. Now you take these images and pass them through a 2D foundational model, like clip and predict features that are 2-dimensional features. And then you lift those features in 3D using sensed depth. So now you have a 3D feature cloud. So at every point, or whatever the occupied points, you have different feature vectors. So our goal here is to predict where should the gripper go in the next time step, in which location, in with what orientation. So what we do to handle the very high dimension of the 3-dimensional space, there are just too many locations to explicitly enumerate. We do coarse-to-fine sampling. We sample some points, we featurize them, we call them ghost points. We featurize them with transformers. Then based on the point that is more likely to contain the end effector, we there sample again, denser points, we featurize them again, sample and so on, and then predict, find the location of the end effector and predict the rotation. And the reason we want to essentially compute this action using this 3D action map, as opposed to just regressing to the end effector's parameters, is because this gives us spatial equivariance and allow us to learn from very, very little training data. Spatial equivariance is that if the scene is translated or rotated, then the end effector prediction will also similarly translate and rotate. This makes you, this allows the model to generalize to translation, rotations, different camera changes at test time. So Act3D essentially gives you an infinite resolution 3D action map through this course to find transformers. And so here is again a zoomed in visualization of the sampling. And when evaluated on established manipulation benchmarks like RL Bench, it has state-of-the-art performance. So here we show it's 10% better than previous work on this kind of easy benchmark, so kinds of benchmark. So Act3D is the blue version, and in a hardened benchmark, it actually does 26% better than the previous state-of-the-art, which was PRACT, essentially doing better from 10 demonstrations, outperforming the previous model when it was using 100 demonstrations. So this shows the importance of the architecture on preserving spatial equivariance in order to be able to learn from very few demonstrations. So here you see the diversity of tasks that are part of this benchmark, and benchmarking is an important problem in robotics. How can we develop algorithms that we can, evaluate and compare with one another? So this is, many researchers are working in that direction as well. And the same architecture also generalizes to the real world. You can give a handful of demonstrations and, your model will be able to perform the tasks. So these ablations show that, we can generalize at test time to different camera views that previous models cannot do. It's important in this course to find sampling to share the same weights. And, all these design choices matter for performance. And we have extended this work to combine, these 3D perception architectures with diffusion objectives. And diffusion objectives really allow you to be multimodal, not only on predicting 3D locations of the end effector, but also predicting the orientation. In the previous model, Act3D, the orientation was predicted with the regression, and we know regression cannot be multimodal. And indeed, we get plus 13% absolute boost with this choice. So in the last, I think, a couple of minutes, I want to describe a second thread. We have seen incredible revolutions in computer vision and natural language processing coming from training large-scale models, large-scale neural networks, self-supervised or weakly supervised on enormous data sets. So how can we scale up robot data, right? We don't have large data sets for robotics. So can we use image and language models to scale up robot data? This is the question. And we have a recent work which we call generation to simulation. We use generative models to create simulation environments, 3D assets, lifting 2D images to 3D, to 3D assets, as I'm going to show, predicting tasks for them, decomposing the tasks, and writing reward functions for each of these subtasks so that you can run reinforcement learning in simulation and automatically discover solutions for the tasks and their sequence of subtasks. Okay, so you don't need humans to design assets, or very few of them, and you don't need humans to code up reward functions for the gazillions or provide demonstration for the gazillion sets of manipulation tasks you may care to do. So here are the three steps. The first is asset generation. The second is using large language models to predict tasks and decompose them. And the third is using reinforcement learning in simulation. So the asset generation essentially takes a 2D image and lifts it into a 3D model using what is known as score distillation by essentially rendering views of that parametric 3D model and evaluating their likelihood using a 2D diffusion model, specifically view condition image model, alongside the reprojection error from the view that we have available. So we are able to generate all those assets by taking random object-centric images and lifting them in 3D. So I think this really can, is extremely helpful on scaling this up and creating tons and tons and different assets that you may care about, for example, for food manipulation and so on. Then you can generate physics for those assets, and by asking the LLM about math and physics parameters, and you see that they behave reasonably inside the simulator, and you can ask LLMs for task reward decomposition. So the way you do that is essentially through prompting. We don't fine-tune the model. We can take a pre-trained large-scale model, prompt it, and ask it to complete the task. So let me show you how the prompt looks like. So you just tell the LLM what are the assets, what are their parts, what are the different API functions. You give one example from only one asset of what are the relevant tasks and what is their decomposition and reward functions. And then the language model can generalize that single example to tons of different assets, their morphologies, their different part structures, and so on. So this is all automated without any human intervention. And then the only thing you need to do is to train reinforcement learning in simulation. So we're able to solve all these tasks without any human intervention, just this prompt essentially generation. So I'm excited because this may give us really a pathway forward towards really scaling up training data for robot learning. So thank you very much. And these are the students that actually did the work: Adam, Theo, Nico, Zian, and Pushkal. And I'm very look forward to the discussion afterwards.
Thank you, Dr. Fakayadaki. So one of the things that's really incredible is you hear all the things about how much data is out there, how to create data. We need to train these AI systems. So our next speaker, Dr. Alex Wong, who's a Canadian research chair in artificial intelligence and medical imaging at the University of Waterloo, is going to talk about just these things, including trustworthiness in AI, which is so instrumental, as you saw in some of the previous videos, of self-driving cars. How do you know that these types of things are going to be actual good ground truths to train your data or to train your systems on? So Dr. Wong, the floor is yours.
Thank you very much. I'm just going to share my presentation. Hopefully you could see it. So thank you very much for the opportunity to, I guess, talk about some of our research in this area. And I think it's great that I'm following Katerina, because following up what she was talking about was generative AI. What today I'm going to talk about is how we're leveraging in our lab generative AI for trustworthy, high-performance computer vision for robotics, especially with a focus on manufacturing, which is the core, one of the core areas of my research area, which is to build sustainable industrialization and manufacturing and foster innovation in that area. And so what are some of the challenges in creating our next generation of robotics? So outside of all the great things that the other speakers have mentioned, here there are three things I would really like to highlight. One of which is that designing these complex machine learning models for tackling the huge diversity of computer vision tasks in robotics, especially for manufacturing, especially getting them in a high reliability and accuracy, is actually very, very difficult and very time consuming, especially because of the need for real-time performance and running on very low-end hardware. Another difficult part, as Katerina has mentioned, is just the difficulty to obtain high-quality data that's necessary to train these machine learning models, which has to see all the different types of scenarios, edge cases, as well as see a huge amounts of different annotations, for a wide variety of different sensors, be it depth sensors, RGB sensors, touch sensors, and so on and so forth. And last but not least, which is especially near and dear to my heart, is that right now there's a big gap in terms of the lack of understanding in how these machine learning models actually behave, making it very difficult to trust their performance, understand what they do well, what they don't do well, where the rooms for improvement are, and so on and so forth. And so one of the questions that we've been grappling with in our research group is, can generative AI help? We've already seen all the wonderful examples of where AI, generative AI has been leveraged. Example here on the left-hand side is, using it based on a text description to be able to generate a photorealistic image. So modern outfits inspired by Van Gogh, fashion shoot. And it's able to generate this very realistic photo based on that particular context. On the right-hand side was a article that got a lot of that went very viral because people were using it. Hey, it gives really great life advice. And what then was uncovered was that it was actually completely generated using large language models. So how can we actually leverage generative AI in a robotic context. And so through our Gen AI for Good initiative in promoting and accelerating machine learning for good purposes of generative AI, we actually used it to tackle different robotics applications. So what can generative AI do for robotics? One of which is we could leverage potentially generative AI to generate multitask machine learning models that can be more powerful, more efficient than what we can do by hand. Another one is, can we actually use it to generate synthetic data for which the computer machine learning models are able to then learn to improve their ability to perform different robotic tasks? And last but not least, is actually very unique, is that can we actually use it to generate quantitative explanations so that we have much better sense in how AI actually makes their decisions, when it can be trusted, and where the inherent gaps and biases in terms of fairness, and of course, how robust is this particular system that we're trying to build. So the first thing I'm going to cover first is our work on generative AI for generating multitask machine learning models. And so like I mentioned before, the machine learning models necessary for computer vision for robotics often comprises of not just one, not just two tasks, but multiple computer vision tasks for robotic operations. So what you see on the top right are things like, where is the center of mass of the object? What is the actual boundary of each object? How are they overlapping? And of course, where are the grasp points? If I had a suction grasper, where would I use it? If I had a finger grasper, where should it grab? And so this becomes very difficult for humans to actually design it in optimal performance, especially for real-time use in low-end systems. And so what we've done was we actually created a generative AI system that allows us to generate multitask deep neural networks for 6 different computer vision tasks for robotic operations. And the surprising thing was that using this generative AI approach, we're able to generate neural networks that run much faster than handcrafted ones we were able to do. So it's able to fit on really small edge devices. It's much, much smaller, uses very little memory for real-time operation in a real-world manufacturing experience, and surprisingly, also gave us better performance across the task. So the inherent model itself has been tailored to be fast, small, and much higher performance across the board. So that was actually great, and we're doing a lot of additional work on this, where we're trying to leverage this generative AI approach to generate different models for tackling different types of machine learning tasks. Next, we're going to talk about some of our initiatives in generating synthetic data for improving machine learning models. And so similar to what Katarina mentioned, we could potentially leverage a generative AI approach to generate real assets, real data. And for us, it's also about generating real scenarios. So what we did was we took a generative AI approach using, as you see on the right, pretty much hundreds of thousands of millions of different cameras, and then using that as well as generated assets and use these digital twins within a metaverse kind of system to continue to generate a huge amount of data under lots of different scenarios using all the different objects, all based on real world physics. And so the result is a data set called MetaGrassNet that we have made completely open as part of our efforts in collaboration with KIT in Germany, as well as Festo, where there's 217,000 different RGB D stands for depth, images across 82 different article types, as you can see on the right. Each one is automatically generated in a real world, physical perspective within a metaverse. Right? Everything is full, because the fact that everything's generated, not only can we actually generate scenarios, we could actually generate all of the annotations for all the object detection, amodal perception, key point detection, manipulation order, ambidextrous grasp labels for parallel jaw, as well as vacuum grippers. We also include real data of 2,300 fully annotated high-quality RGB images, so you can actually validate that whatever performance you achieve in this virtual world using synthetic data is actually applicable in real-world general situations. We've divided into 5 different levels of categories to allow our robotic systems to then be able to learn over time and improve itself. And we've also included an unseen object data set to allow us to evaluate different object and layout properties. Because in a lot of situations in the wild, your system might have to adapt to new types of objects it hasn't seen, new types of scenarios. So we'd like to be able to evaluate and make sure that the AI that we build is responsible and also trustworthy and robust and reliable under these kind of unseen situations. And so here's just examples of what the data looks like. So you have all the bounding box information, you have all the labels of what type of object it is. You have both on our left-hand side, the RGB, so the red, green, and blue camera images captured using machine vision camera. And on the right-hand side, the depth data. Bottom left is a 3D rendering of what that might look like. And on the right-hand side are the different grasp points that we actually fully include for building these kind of systems, all generated synthetically. Then last but not least, what we've been exploring is, can we actually use this generative approach to generate quantitative explanations to better understand how these machine learning models for robotics are actually performing? So just to give a bit of context, so today, a lot of systems you have training data, you have a machine learning process, and it'll learn some kind of machine learning model that makes a decision recommendation. But to the user, it's a very big black box. So why? They don't know why it did it a certain way, why it made a certain decision, right? Why did it pick certain things up a certain way? Why did it think it's a can versus a box, right? Why didn't it think it was something else? When does actually the AI succeed? When does it fail? When can you actually trust its decisions? And most importantly, how do you actually correct the errors that it makes when you don't know exactly how it's thinking? So in the realm of explainability, or XAI, explainable AI, you do still have trained data. You train a model, but the model itself is explainable with an explainable interface. So you know exactly, understand why it made a certain prediction decision, why it didn't, why it's successful, why it failed, why and when you can trust it, and why it erred, so you can actually fix that error. And so we kind of moved it from the general XAI realm beyond just a buzzword, from theory into actionable insights, from proxy to actual direct explanations. So with quantitative explainability, you're given not only the exact reasons and factors the AI actually made the decision, but also the full quantitative justification as to what is the rationale behind it. So in this case, as a simple example, here is an image classifier neural network, right? And it's being tasked to determine, what object it is, right? And so on the left-hand side, you see a jet plane and you see a meerkat. And so the model needs to make a decision. But with quantitative explainability, not only do you get the decision, you also get the explanation. So on the top middle, what you see, the explanation for the jet plane is that it was looking at the front of the jet plane and the wings. On the bottom, it's looking at the face as well as the front chest of the actual meerkat and not looking at its surroundings to make a decision that it's a meerkat. And it provides full justification around it. So from the top, it says, based on this explanation, the model predicts it's a warplane with 98.7 certainty based on the factors that it's mentioned, because otherwise it actually thinks it is a parachute with 23.5 certainty. And if you could kind of just ignore the region that it highlights as an explanation and just look at the surroundings, all you see really is sky. And so it wouldn't be a stretch of imagination that it would think it's a parachute. Similarly, on the bottom side, it explains how the model predicts it's a meerkat with 97.4% certainty by looking at the face and the chest, because otherwise it would think it's an ostrich with 67.6% certainty. And again, if you were to put your finger and cover up the meerkat, the highlighted explanation with the surrounding area of grass and so on and so forth, you would actually potentially mistake it for an ostrich. So how does this explainable AI, quantitative explainable AI, relate to robotics? Well, what we did was, once we created this explainable technology, this approach, we actually used it to understand how our grasping robot deep neural networks is actually thinking, making decisions. In this way, we can better identify how we can actually improve it. So here's an example of what we call second-order explainability, where based on the quantitative explanations for every single sample within the data set, we then analyze it to understand what the trends are, what the concepts are, that it's having trouble or it's doing well. So in this particular case, what you see are clusters that show different levels of focus by the model in making its decision. And what you see is, when it doesn't do so well, it actually largely focuses on the logo, instead of actually looking at the head and the body of the actual drill. And as a result, it makes a lot of mistakes in those particular areas, especially the drill head. Whereas if you take a look at another cluster, it shows that in situations where it doesn't actually see the logo, doesn't see text, it actually does much better when dealing with the actual back face of the drill and the face of the drill head. And based on this insight, we're able to say, okay, the model is having this struggle because it's looking at the wrong information. And as a result, what we did was then train a model so that it doesn't focus on the text, and lo and behold, we're able to get much better performance. And this is a good example of where explainability not only gives you much better trust in the AI system itself, it could actually help you improve the system. So just some final thoughts. So, there's tremendous real-world challenges to achieving trustworthy, high-performance computer vision for robotics. Fortunately, generative AI can be a very powerful tool for enabling improved computer vision for real-world robotics deployment, and the benefits just really outweigh the challenges with designing and operationalizing trustworthy, high-performance computer vision for powering the future of robotics. Thank you very much. And I just want to also thank my team in the Vision and Image Processing Research Group at Darwin AI, as well as our collaborators in KIT, as well as Festo.
Wow, what a great panel. You've all covered all the major topics that we've been struggling with to bring AI into practice and to be reliable, trustworthy. And some of those major underlying projects, I'm just going to talk to wrap it up and summarize. Data. How do we get that data? How do we get that trustworthy data? How do we generate it? How do we find confidence in it? Also looking at the model. So one of the first questions I wanted to ask the panel is, we've all talked about in some of the things about delay and latency and making decisions, the underlying models, how in edge devices, getting them to edge devices. Do you see in the future that we're going to have AI that doesn't have millions of parameters, and that we really can have generative AI that is cost effective and reliable? So I'll just throw that one out there, and I don't know who'd like to start, but just talking about what you think about the models themselves. What's the future of these models, and what are some of the things, the barriers that we need to get over, and how you envision it? So I'll throw that out there. Who'd like to start?
I'm happy to make an initial comment. I'm not sure it's useful to talk about how many parameters models in the future will have or not, but I think some characteristics of the inference time, I think we can talk about. And I think we need to talk a lot about the energy cost of inference. At the moment, we're running on really expensive, power-hungry hardware. That's fine for a lot of the work that we do, but if we want to put it out into the field, it's got to be super quick to do the inference, and it's got to be able to do it with the minimum amount of energy. But I think there's some really hopeful signs in what you see in, like, this is not a modern phone, but in modern phones, you've all got sort of neural engine chips in them, and I'm sure that technology will go gangbusters into the future. So I think that, to me, is a very promising sign.
Thank you. Anybody else want to chime in on that one?
I'll add to, I guess, what Peter said. I mean, I completely agree with every single point. I think the other key thing is that just more on the model side, there's actually a huge movement, typically called the tiny ML movement, or efficient ML movement, where we're all trying to actually design better models. And in the example I gave you, leveraging maybe generative AI to actually help us design better models that can actually fit better into these low end, cost-effective, energy-effective edge devices.
Okay, great. The other thing I wanted to talk about is, so much of what we do is vision based, and how robots that's the theme, right? Robot vision, we're talking about that. But one of you was talking about, the question of car companies, for instance, and we have questions in our chat saying, what's the general opinion of experts when cars will actually be fully autonomous and safe? So I want to throw the question out there about the sensors themselves. Some departments of transportation around the world are saying, well, you know what? We have Bluetooth that's communicating live. We have LiDAR and radar. We won't need vision sensors. And yet we know that vision is so important in robotics. Who would like to comment on some of the future of vision sensors? Go ahead.
Maybe I can jump in. I think your comment, Karen, reminds me of Elon Musk's comment on the fact that LiDAR-based approaches to self-driving are doomed to fail. Maybe as a little bit of context, the main sensors which are used in robotics and partially also on self-driving would be LiDAR and radar, for example, which are measuring essentially distances. Vision, which is a very rich sensor, is measuring appearances. It's not really getting the depth if you use a single camera, but is measuring appearance. Another popular sensor, which nobody talks about, but is always there in application, is an inertial sensor, inertial measurement unit, which is measuring acceleration, rotations, and so on. We have one of these sensors in our iPhone, in our pocket. So it's very pervasive sensor. In my opinion, there are these sensors I'm talking about are very complementary in nature. Again, LiDAR, will measure distances, will be an active sensor, so it's projecting light in the environment, which means that we'll be able to perform even in the darkness. Will not need the natural illumination. We'll be able to perform in all sorts of conditions. Camera instead is a sensor for which you get a lot of rich information, but it's very hard to extract insights and information out of camera images. And again, in darkness and low light conditions, cameras are not going to be very useful. So it's a long answer to say that, these sensors to me are very complementary in nature. So at the end of the day, what you have to pick, more than saying this is the best sensor, you have to understand what is the best sensor for a specific application. There is clearly a trade-off in terms of performance versus cost and versus power consumption. You have to understand for your application, which side of the spectrum you're in. For example, if I want to manufacture a cheap domestic robot, maybe I do not have power. I do not have the cost of I cannot incur the cost of putting radar, putting lidars and so on, 3D lidars and so on. But maybe I would prefer just a cheap camera. If I want to do self-driving, maybe it's worth putting extra sensors if what you're trading off is safety of the passenger, right? Maybe incurring extra cost to make the passenger safer is probably the way to go. And last thing I will say, and I will pass to the others, is that somehow there is this argument that if humans can do perception with 2 eyes, essentially robots, vision only, approaches will be sufficient for the future of autonomy. I mean, that argument, I think, has a logical fallacy in it, which is we're assuming that, the type of compute we do for AI and the type of algorithms we use in AI are the same that, our brain is running, which is a huge assumption, right? So, and also, just if you look at the hardware, the human eyes will have much better dynamic range and much better properties compared to the cameras we have right now.
Thank you.
Sorry for the long answer.
No, that's great. Katerina, can you help us answer our panel? One of the comments came in. We're asking, what's it going to take to make them fully autonomous and safe? What's the projection?
Yeah, okay. So just to follow up on the previous answer about visual sensors, I mean, we do have Tesla cars right now running only on cameras. So I think the huge benefit of a camera is not, okay, the pixels that come in. There are fantastic architectures pre-trained on those images because, the value of a sensor is what you do with a sensor. So you need learning to map the sensory readings into outputs. So with the image that comes in, fantastic 2D foundational models trained on, millions and billions of images, you will have them for free. So I definitely believe in the cameras. We have them, tons of them packed on my mobile phone. They're cheap and they're everywhere and so on, right? Yeah, and so that's number one. Number two, I mean, one projection I've heard from a very, field expert is 2027. I do believe that they're quite safe. I think what we need to realize here is that it's not an absolute scale. They need to be safer than humans. And depending on which one of us and our, moral, let's say, inner soul, people may want to be, 5 times more better than humans or 10 times or 100 times to be able to deploy it on the road. I mean, as far as I'm concerned, a life of a relative of mine has already been saved by the automated stop of a car. So I would definitely, and I'm somebody who bumps the car all the time, left and right. So I wouldn't be at all surprised with cars being better than humans very, very soon, right? And they're already, but I mean, I'm pretty sure there are some legal, contracts that we need to go beyond. And all this assumes benign weather conditions. I'm not exactly sure what happens. Yeah.
So what I love about your answer is, we're putting it relative to how humans drive. And I resonate with that because I'm here in Boston, Massachusetts, which is, every 15 minutes there's an incident or a crash. So yes, is it going to be perfect? Maybe not, but at the same time, is it better than the human? So I think that was a wonderful answer. Is there anybody else who wants to chime in on that before we move on to the next question? We'll go with Peter first, and then we'll go to Dr. Wong.
So this issue of safety is the key one, as both Luca and Katerina have mentioned. I mean, the stats are pretty terrible. It's 1 million people a year killed, 100 million a year injured. So you know the cost of the current way of driving is pretty terrible. I'm probably with Elon Musk and Katerina in thinking that there's an existence proof that it is possible to drive a car using only camera sensors. Execute and nowhere near as good as what we have in here, but I think that's a matter of a short number of years, way less than a decade. So I think safe self-driving cars are inevitable.
Alex?
So just really 2 quick comments. One is I think for me, just having also worked a lot in automotive, is that the notion of self-driving car is always very glamorous. But I guess to everyone's point, you don't necessarily need fully self-driving cars for you to already get all the benefits, like ADAS, right? We talk about assisted driving. Like we all love assisted driving. There's an AI component that's already helping us be more safe. I think working our way, just like scientists, right? Working our way towards a solution is great. It could happen, but we still reap a lot of benefits from the technologies that we get built. And the last thing in the comment is that when can it be safe? I completely agree with what Luca mentioned in terms of it really requires a multimodal kind of approach, right? Using the right data, right sensors for the right problem, especially when we're talking about autonomous driving. I'm from Canada. When everything looks white outside because of a blizzard, and there's huge, like, just snowflakes dropping nonstop, a lot of sensors that we are used to, they just don't function on those kind of certain situations. That's where having different sensors, as well as, of course, a human ability to intervene when necessary becomes very valuable.
Okay. And before I call on Luca, I just want to let you know that I now know that I'm in the right research area because my own research is in the field of removing weather anomalies from images for driving. So thank you for all reaffirming that I have a future. So I'll go ahead and call on Luca. Go ahead, Luca.
Yeah, just like, a second comment, just a follow up about the question on the timeline for full autonomous driving. In my opinion, it's not a question of when, it's more of a question of where, right? So we spoke partially about weather, but in general, different geographic locations might see self-driving, at different times. For example, today, you can probably go to San Francisco and get an autonomous taxi, and that will work just fine. If the question is about when we're going to see localized deployments of self-driving, fully autonomous self-driving in specific areas, I think I can answer that today. Today, we already have that kind of deployment. You can switch on Tesla, autopilot in specific areas, and trust it. You can take an autonomous taxi in San Francisco. If the question is when we're going to get level 5 autonomy, in which you can drive everywhere, with your self-driving car without need of any intervention. For example, you can drive, anywhere in Italy, which is where I'm from. I don't think that will happen in the next 10 years. So sorry, to be a little bit more pessimistic than the others. But in my opinion, handling corner cases for self-driving is pretty much the same as requiring general intelligence or general perception for our robots. And either we believe that we're going to get general, very broad perception capability and very complex reasoning for our robot in the next 5 years, or otherwise we have to be more pessimistic about, self-driving. Happy to be proven wrong. We'll see in a number of years, I guess.
So that leads us to a more broad question now. A lot of the things that we've talked about today is, human perception versus robot perception and trying to get the two closer with less latency. So I'd like to open it up to more about, what do you think needs to happen, or do we need more robots to be just like humans and be able to act as quickly as humans, to think and reason like humans? So let's open it up. How do you feel about just the fact that we're trying to get, I would almost say digital twins, robots to be digital twins of humans? So I'll open it up. What do folks think about the future of trying to emulate real human thoughts and behaviors inside the robots?
If I could just comment about, I think the behaviors are really important. If you had a robot co-worker that was sort of sitting next to you at your desk, or working next to you on a production line or on a farm, I think there are some things that you would expect of it. And I think sudden surprising motions, sudden surprising long pauses, I think would drive you absolutely crazy in a very short amount of time. So it's sort of been one of my pet peeves of late, is robots that just appear to go dead for a period of time and then suddenly wake up and start moving. I think it's going to be very stressful for people to work with robots like that. So I think that's one thing we have to work on and eliminate.
Okay, and it's funny you say that, because think about how when we're running programs or our keyboard doesn't respond right, people want to bang on the keyboard, and you can't bang
Exactly right.
do that.
Yeah,
so,
because we have an expectation of how the system normally behaves, and when that's not met, then yeah, we get cranky.
Who else would like to comment on that? Okay.
Yeah, so maybe so you asked what we need for perceptual capabilities to match human capabilities. Do you agree? Yeah. So basically, maybe what you're saying is, when is a ChatGPT moment for computer vision? Something like this, maybe you're asking. So one thing that I believe, but I'm not super certain, is the following. We may jump to very different architectures for computer vision. We know that the brain does a lot of decoding, a lot of rendering. There is encoding comes from the image to the percept, and then the process back the render and generate, and they get feedback, and then and you encode again and decode again and so on. And our perception architectures right now are purely feed forward in nature. And the reason is that we couldn't get generative models to work, and now researchers were able to get image generative models to work. So I do believe that we may jump to a very different generation of architectures that they perceive videos not just by encoding every frame and wasting so much compute at every frame, but rather rendering what they have built already, the scene, the 3D scene, they render it and match, and only update where the change happens. So we go from encoding alone architectures to encoding and decoding architectures. Yeah, this is what I would hope for.
Okay. And so another one, you've talked about a lot of practical applications, but we've got young people coming up that are being brought up in AI generation, and you see so many things in the news about bias in AI and mistakes that AI made, or the trust people have in it. They're selling products, therefore people that are consumers buy this think, well, it must be good because the AI says it's 99% accurate. What types of things do you see AI being used for in education to train the next generation? What do we need to do to make sure that our future leaders and students understand the fun, not just how to build these models, but really the right questions to ask? So I'll throw that one out there, that question out there. So the future of AI in education, what do we need to do and where are we with it?
Sure, I'll start. I mean, mainly because one of my main focus has been on trustworthy AI, responsibility, and part of it is just as educators at a university. What we are starting to do now is incorporate more data literacy. So we always talk about data literacy, understanding the data, what does it mean? But now we're also trying to do a lot more on AI literacy, right? A lot of times people use AI exactly the way you mentioned. They'll just trust. Back in the day, nobody just trusts AI at all. That's one. Now it's gotten to the point where everyone just takes it as, ChatGPT told me, right? It must be correct, right? That kind of mentality. And to use a large language model in its current state as the source of truth and knowledge becomes a bit of a challenge, right? And so, but they could be actually extremely helpful in assisting us, being co-pilots in things that we do. And so now we're starting to educate our undergrad students and so on and so forth, and hopefully beyond, and executives and so on and so forth, to really understand what they can do right now that could be really powerful and game-changing for their industry, for their personal usage, for social good, and what are some of its current limitations, so that people are able to avoid using it for purposes that it's not really great for or suitable for.
Mm-hmm. Yes. I also wanted to mention, Peter, you made me think about when you were talking about your hand-eye coordination. There's so many opportunities. The minute you said that, I was like, there's so many opportunities, like children with autism or different types of different abilities, using tools like this to help them, aid them in training and education. So using the AI as actually to help bridge the gap rather than trying to mainstream all of our students as, we all learn differently. Why not have the AI be able to tune in and be able to help us with that? Do you have any comments about perception, or have you thought about the future of in some of your work like that for education?
I haven't thought of it in those terms for education, but I mean, guess the AIs are just another point on the spectrum of the way people think. At the moment, I don't think we think about AIs in that particular way. So, in some ways, they're probably be more literal, maybe more imaginative than humans are for some things. But no, it's not something that I've thought deeply about.
Is there anybody else that wants to talk about AI in education in their realm?
Yeah, can I maybe get I would like to comment maybe on both the previous question and this one, in education, the previous question was about human versus machine perception type of things. And there is this beautiful theory that is called the uncanny valley. I don't know if you heard about it. It's this idea that as robots are very far, different looking from humans, we're not too scared of them because, we don't recognize them as humans, but as they get closer and closer in appearance, there is a valley in which the way we like them, and the way we're scared about them, goes down in the sense, we are more scared about, robots which are looking like humans, but they are not quite there. I think we are in the uncanny valley of language and perception as well. We are getting close enough that these things, we are reading a lot into what AI is providing us, in the detection of AI and so on. But these things are failing in a way that we don't really understand. And I think the parallel with the uncanny valley is kind of a fitting one in a sense. We're not there yet. We're not yet at the level of human perception. In terms of education, I believe, if I think about the way we teach today, for example, engineering, at the end of the day, we're teaching, for example, equations, formulas, principles, and so on. But we don't care too much about the students memorizing, formulas, memorizing equations. We're trying to instill or, to convey a mindset, which is the mindset of how to approach engineering design, how to design systems, how to think about safety, and so on. And I think we have to do the same for AI. In a sense, we have to still expose the students to the machinery of these AI tools, but we have to go back to the principles and understand that these are just tools. What we want to teach the students are not how to prompt ChatGPT. We want to teach what are the implications, or what goes into thinking about an NLP, natural language processing system, which can be used for for society. That's all I have.
Thank you. So let's talk more about, we've talked about using AI for good. In the future, a lot of the types of things that we see people that are using it not for good. So, I guess I'm going to ask more about the trustworthiness and explainability, because as we develop more and more AI, how do we make sure that, we've talked about self-driving cars and things like that to make it safe, but that's safe in operation. But how do we use it so that it's not misleading us or actually harming us? Does anybody want to talk about the trustworthiness or explainability, how important that is?
I'll start. So I guess as far as my research working with others in the realm of trustworthiness and explainability, one of the key things is to really leverage it to have a much deeper understanding into the AI models that we're building. And the key things that we always want to do is, the obvious one is making sure that whatever it's doing, it's actually doing it for the right reason. Right. So for example, building AI for understanding whether somebody has a certain disease, right? Being able to confirm and validate that, hey, it gave this recommendation that this person had respiratory problems because of, calcification of the lungs, ground glass opacities. That's great. But a lot of times that we don't use it for, and I've been kind of advocating for it, is using it to understand when it makes the right decision for the wrong reasons. And that's where you understand where the system might be misleading in terms of saying how good it is when it's really not that good. So one example I had was for autonomous driving, right? There was a system, the RMSE, for those who know, root mean squared error for driving, for steering, looks great, looks beautiful, right? Almost perfect. Then we did use explainability to understand, how is it making decision? Why is it so good at driving? So we found that it was never looking at the road. It was not looking at any of the street signs, right? It knows nothing of the rules of the road. All it did was identify obstacles and try to avoid it and not crash into it. And that's how it's steering so well. It's essentially playing reverse bumper cars, right? And so there are situations where it does really well, but the rationale behind it, like if I tried to, sell you a car that tells you, hey, it'll be perfectly fine, it's just trying to avoid crashing into things, right? You'd be a little hesitant. So that's where, having this explainable AI and trustworthy assessment becomes really valuable to really understand the systems and whether or not it's actually meeting your own expectations for how it's supposed to be performing.
Okay, terrific. Anybody else want to comment on how important that is right now? Okay. So we see some questions coming in from our audience, and I don't if one of them is asking, can we derive uncertainty from deep learning models and use it in state estimation, belief propagation, like in traditional models? So is there somebody? I see Luca nodding his head. So Luca, do you want to take that one?
Yeah, there are a couple of things that come to mind. I guess, there is Bayesian deep learning, in which you're reasoning over probabilistically, you're reasoning over outputs of the neural network, and you do some uncertainty propagation from the weights, to the output. So Bayesian neural network is definitely a keyword that I suggest looking into. Right now, a framework which is getting quite popular is another alternative to, let's say, quantify uncertainty or provide guarantees on the output of neural network, which is called conformal prediction. In conformal prediction, rather than saying I classify this as a cat, and I give a single output, you allow the network to provide multiple outputs, and then you guarantee that the correct answer is among one of these outputs with high probability. So look for conformal prediction as a keyword. These are the obvious ones that come to mind at this point. I'm sure there are more.
Thank you. I want to jump back more to questions about, you talked about mean square error. And I laugh because it's like people use it, but we as researchers, we know it's like, okay, that it's not really indicative of how great the performance is going to be. So Peter, I'm going to come back to you about real world metrics and performance. How are you looking at all the performance metrics out there? And again, I know you've developed some things looking for graceful and reliable, but can you comment just in general how important metrics are and how important they're going to be in the future for all these systems for us to be able to truly evaluate them?
Yeah, metrics are really important, and particularly in this era of deep learned systems. The performance of learning systems is generally done in terms of some percentage accuracy, and we publish papers each trying to do better than the previous papers in terms of some particular metric. And if you look at what's happened in the computer vision community, since it met deep learning, I think that fabulous progress over 15 years has really been driven very strongly by metrics. You can argue whether the metrics are the right metrics or not, things like IOU and others. But the advantage of a metric is that it allows progress to be made. Progress can be measured and it drives progress. In my own area, I focused a lot on manipulation, and for a long, maybe this is 5 to 7 years ago, there's a lot of concern about what should be the metric for grasping, for robot picking things up. What should it be? People tried all sorts of measures, and the one that eventually succeeded was really simple. It's how many times did you actually pick a thing up per hour? Because in industry, that's what they care about. Really don't care anything about the algorithm behind it. It's how many times an hour, how many things you can pick up in an hour. It's a fundamental productivity measure, really easy to measure.
Yes.
And it's endured because it was simple, and it has directly related to economic value of the robot system.
Yeah, and I was going to jump on that because Katerina talked about, when you did your presentation, Katerina, you said, we compared to this simple database the simple benchmark. Can you talk more about the benchmarks, like as you see them? You mentioned in your presentation, you had some of them, but as we move into, we publish a benchmark or we publish a database, those have to be dynamic, don't they? Don't they have to be constantly changing, evolving, and becoming more complex as AI? So can you talk more about the importance of these benchmark databases?
Yeah, so as Peter said, computer vision has had a series of benchmarks. When I entered, the one benchmark was ETH, had only 5 classes, 5 categories, very simple. And then we had Pascal, 20,000 images. And then we had ImageNet, 1 million images, and then Coco with masks and so on. And now the amazing thing is that although till Coco we had more and more labels and annotations, now we have entered the era of weak supervision, where we have images with just captions and so on, or weakly supervised annotation or bounding box generation. I mean, of course, computer vision is very easy. You have a model, you develop it, you run it in the benchmark, you get a number, you compare. With the robots, it's not that easy, okay? No. So there are 2 things you can do. Either you need to work in simulation with all the problems, because you need first to create the simulation environment. This on its own is a research goal, right? How do you make a good physics simulation of cloth and water and plugging the laptop or whatever wire, whatever manipulation that's do, and then you have the real world. And one thing is what DARPA did, right? It says, okay, you guys need to use your robots to do these tasks, and you're going to use the same test bed, which is totally not easy and scalable and easy to iterate on. So benchmarking for robotics is an open research problem. Right now, what we do is we have one thing to be a simulation to test algorithms and say, look, my algorithm can learn, has higher accuracy with fewer training data than yours. And then a completely different thing is what you need to do to train to sim to real transfer, where you really need to scale up simulation and augmentations of those training environments, or only train in the real world, and somehow you're going to show in your own personal data set the results. Now, at the same time, we have industries having test beds that academia doesn't have access to. In self-driving cars, we see this way more. I mean, we have reached the point where academic research cannot compete because maybe the technology is mature, so that you really need an actual test bed to evaluate your algorithms on. So I'm not sure I have a very good solution of what we need to do in the future.
Okay, well, that was a great answer. That was actually a fabulous answer. So thank you for that. One of the things that I've been working on, I create a lot of databases. And the only reason I started creating my own databases was because when I went to benchmark some of my algorithms, I would find, just like Katerina was talking about, I was like, what do you mean there's only 5 categories? Or it wasn't accurate for the real world application that I was targeting. So yes, I think that everything we've talked about today, you're all spot on. And I want to wrap up by asking, is there any closing comments that I'd like to go through each one of you, and we'll start with Peter. Closing comments of just summarizing or finishing up, or what parting advice you have for those aspiring to get into this field, or aspiring researchers or educators of the future.
All I'd really like to say is that these modern AI techniques are absolutely going to radically transform the field of robotics. I think it's what it's going to take to make robotics a sort of general purpose helpers of humans that we've imagined, dreamt about, been driven by for the longest time. For someone like me who kind of grew up in the classical era of robotics, I'm not sure I'm entirely comfortable with it, but certainly all the students, all the postdocs in my lab, this is what drives them. And to be honest, I think it is what will make robots what we want them to be.
Luca?
Maybe I'll just mention what I typically say on the first lecture of my undergrad course to the students when I start talking about robotics. I want to stress the fact that it's a very exciting time for robotics. We're at the point in which things are starting to work, but not quite. There's still things to do. And whatever we do in the community, being robotics, computer vision, ML, and so on, is going to have a huge impact on society, on our life, everyday life, starting from today. So if you're starting, if you're looking at different research areas, just know that, robotics is a very exciting field, is a very inclusive field. So feel free to join, be in touch if you want to learn more.
Thank you. And Katerina?
Yeah, so maybe what I want to say is that I want to say what my chair in my department said in a personal conversation, that in 1990s, we thought that the solutions to humanity will come through technology. Now technology has advanced and social problems have not improved. I think AI will do super well, is doing super well, and will be doing better and better and better. I think we really more need to focus on social good. And I don't think the obstacle there is that AI is not competent enough. I think it's more like political and social, forces. Mm-hmm. And we really need to take that second, AI is doing awesome. And the social good part is what we need to, protect more.
Thank you. And Alex?
Sure. On a similar vein, for me, anyone who's trying to get into AI, AI is getting more and more powerful. It's not going away. We're using it every single day. I'd be hard pressed to ask anyone who's text messaging or typing email and doesn't leverage, autocomplete to a certain extent, right? So I think the most important thing for people to think about, especially the, next generation, is when you're building these powerful AI models, you really should start thinking about how they work, really understand deeper understanding into how they behave and how they affect others, as well as using it in a more socially responsible way. What are the right applications and what aren't?
Thank you. I want to thank all of our experts here today. I think this was a fabulous in-depth talk, and you all have been contributing so much. And I'd like to turn it back now to our host, Guillem. So thank you.
Oh, Karen, this was fantastic. Big thanks to all our speakers today, Alex, Luca, Katerina, and Peter, as well as all the participants for making it such an interesting discussion. And we had lots of great questions and amazing insight into computer vision for robotics. And we would like to invite you to check our AI for Good program online to see more robotic sessions that may be of interest to you. So on October 24th, we'll be having an AI for Good robotics webinar on rehabilitation robots, advancing physical therapy for improved health outcomes. Or in November 7th, we'll have a Robotics for Good Innovation Factory session highlighting the startups supporting the SDGs. So we are very much looking forward to engaging with you in our upcoming events. And this is the end of this section and the start of the networking in the AI for Good Neural Network with the panelists and participants for the next 10 minutes. So see you all in a couple of minutes. And now I will give back the floor to Anna for the closing information. Thank you very much.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.